Welcome to Chapter 18, Part 1. We're going to look now at aromatic substitution reactions. We're going to look at substituting the hydrogen on benzene for other atoms and functional groups. Now, when we think about these reactions, we have to remember that benzene is super stable, so it does not react the same way other alkenes react, right? If you add Br2 to an isolated double bond or even conjugated double bonds, you will get the addition of bromine across that double bond. However, if you add that to benzene, absolutely nothing happens. So we have to, what's a good way to say this? Be a little more creative. So what we find is that if we have a certain kind of catalyst, we can get this to react. Now, it doesn't react as an addition because we still want to maintain aromaticity at the end. It's hard to break aromaticity. The observed reaction is called an electrophilic aromatic substitution, and the majority of what we see in this chapter is going to fall in this category. We'll look at one nucleophilic aromatic substitution at the end. We're going to go through all of these reaction types in the first half of Chapter 18. We're going to learn how to add halogens, nitro groups, sulfonyl groups, R groups, and carbonyls with R's to make ketones. Okay, now each of these reactions is going to have 3 steps. All right, so we're doing EAS. We're going to look at the mechanisms, and we're going to be interested in how to make a good electrophile. You need a really strong electrophile to attract the electrons out of the aromatic ring. You are going to do the actual substitution. And then in the final substitution, okay, I know there's too many T's in that. And then finally, you're going to regain aromaticity. Now, what's cool about this is every single one of these reactions, this step is going to be the same. So this will get quite repetitive, but that means you do need to pay special attention to the first and last step because that will be different for this set. We're going to start off with halogenation. Now, when you think about halogenation of a double bond, right? When this starts, you have the electron density in that pi cloud attracted to the bromine's temporary dipole moment, and you make a halonium ion. But this is not a strong electrophile, right? We're relying on temporary dipoles here. So we need to make this into a better electrophile. We need something that's going to be more electron poor than this Br. So that's where our Lewis acid is going to come in. We're not actually going to use Br and Fe. We're going to use the Lewis acid catalyst, iron tribromide, FeBr3. Remember, a Bronsted acid is a proton donor. A Lewis acid is an electron acceptor. So if we think about this reaction, and we're going to do the mechanism on the next slide, we're going to take benzene and we're going to treat with Br2 and FeBr3. This is the first set of reagents that you need to memorize. The product that we are trying to make is bromobenzene. So let's jump into the mechanism. So the first step we're going to be doing, so if we numbered this, let's say 1, 2, and 3, the first little step here is you're not even going to see the benzene yet. The bromine, right, lots of electron density on this bromine, is going to interact with iron tribromide. Right? The iron has an empty orbital that is going to accept the electrons from the bromine. All of these steps are reversible. So you're going to wind up with this iron tribromide bromine complex. Right? When we put those extra electrons on iron, it has a negative charge. The bromine has a positive charge. Right? The iron is pulling that, well, not the iron. The bromine is having to share those electrons. So what it does is it causes this bond here to break. Right? So we wind up with Br plus. Now this is a very strong electrophile, and we also have FeBr4. This is going to come back in a little while because remember, a catalyst is not used up in a reaction. So we will see that guy again. Now, if we go to step 2, we have our benzene ring, and we have our extremely electrophilic bromine cation, much more potent. That is going to attract the electrons from our aromatic ring. Now, what we draw next is important, and we are going to draw it over and over again. You are going to have your bromine added to the ring and a plus charge. Breaking aromaticity isn't ideal, but it is stabilized by resonance. And this set of resonance structures where that plus charge is shared across the ring. So let's draw all of our resonance. If resonance is something you struggle with, this is a great time to practice. All right, and then one more. I most certainly will ask you about sigma complex, or about these resonance structures. And so you need to feel comfortable reading them. If not, maybe drawing them all the time. So these 3 resonance structures are referred to as the sigma complex. Right? The sigma complex is important. I am not going to draw it out every single time we do this reaction. But if you are looking to practice resonance, that would be a good time for you to add those into your notes later. I am going to draw them occasionally, but sometimes I will abbreviate. Then the final step here, to regain aromaticity, something needs to grab the proton on the carbon with the bromine. In this case, what is going to act as your base is your FeBr4. And it has a negative charge. The iron is super happy to let go of this bromine. So the electrons holding the bromine to the iron, let's be creative here, there we go, pick up that hydrogen. Then those electrons flow back into the ring to regain aromaticity. And in that final step, we have made bromobenzene. Now, this is the only product you make because if we looked and tried to do an addition, like with an isolated double bond, this product is way higher in energy than this product. Re-aromatization is going to happen. That's what you're going to get, and so you get the substitution product. There are other Lewis acid catalysts you could use, but if you're using bromine, you want to make sure it's a tribromide. You're typically going to see with bromine it being paired with FeBr3, at least from me. Chlorination follows the exact same mechanism. except instead of iron tribromide, you're going to use aluminum trichloride. This is going to follow an identical mechanism, so I am not going to write this one out, but every time you saw bromine, you replace it with chlorine, and iron is replaced with aluminum here. This is a great reaction for halogenating a ring, specifically bromine and chlorine. Fluorine doesn't work, it's too violent. Iodine doesn't work, it's too slow. So you're going to see this with bromine and chlorine. And you do have the mechanism, of course, written out, at least step 2 and 3 here. What I want to point out, because you may see this depending on the books you're looking at or the questions, if this bond this bond right here breaks before the nucleophilic attack, or if it happens in a concerted method once you've made your little Lewis acid complex, you can show that either way for me. Some people put it together like this, or break it up into 2 pieces like this. I'm fine either way, right? You see they kept it together here and did it all as one step. It's fine with me, whichever way you practice it. As long as you're practicing it, I'm pretty happy. All right, now what you're going to notice in the next several reactions we learn, you're going to have this same basic second step. You're going to have the nucleophilic attack of your potent electrophile that you will have to learn how to create. You will have a sigma complex, right? That's stabilizing that carbocation that you formed. And then you will have some sort of last step where a base removes this proton. Now, depending on the reaction, this base varies. In the halogenation, the base will be either the FeBr, 4, or the aluminum would be AlCl4. Either way, that's going to act as your base, and it's going to regenerate the FeBr3 or AlCl3. We're going to go over one more reaction in this video, and that is sulfonation. Sulfonation is going to add an SO3H. Now, this is going to use fuming H2SO4. Now, it's important that it's fuming, and we're going to talk about why. The first step of this one's actually pretty easy. You don't have to create the electrophile like you did in the last reaction. The fumes, when you have super concentrated H2SO4, and that's what fuming H2SO4 is. It's saturated sulfuric acid. This is what the fumes are actually made of, sulfur trioxide. This is the potent electrophile, right? So instead of, instead of H2SO4, that's not a very good electrophile for this. The SO3 gas that is being released from a very concentrated H2SO4 solution is a potent electrophile, and that is what is going to be attacked. So if we're looking at the mechanism, step 1 for you guys is just knowing that this is the electrophile. This is what you need to know. And then everything looks very similar in the second step. We're going to attack. I'm going to point down this way so I have room to draw my sigma complex. Then we have S, and I'm going to abbreviate this a little bit, O minus. We have our plus charge here. Then you are going to have your other two structures. I encourage you to practice making those on your own. The last step, what is going to act as the base here? We don't have iron tribromide. This is an extremely acidic solution, so you don't want to show a strong base. What is going to act as a base is going to be water, because even in the most concentrated of acid solutions, there is water. It is a solution. It is a saturated solution. So you should know that the base is water, and that is how you are going to regain aromaticity. There is one final step here, and that is to protonate. You're in a very acidic solution, so you can show that proton coming from any. You can do H2SO4, you can do H3O+, you could do H+. It's very acidic, so whatever you decide to do there is perfectly fine. Right? It's a very strong acid solution, so hydronium makes total sense. H2SO4 is fine as well. And that is how you're going to get SO3H. So in this reaction, what's really important to add to knowing about the sigma complex is that you have the SO3 as your electrophile, that water acts as your base, and that in your final step, or you have an additional step where you have to protonate this guy. In the next video, we will talk about the next reaction. Klein does show you that sulfonation is reversible, and that can be helpful for some synthesis. You can put this on, block this position, take it back off. I don't focus on the reverse reaction of sulfonation, so you can just keep going from here, and we will hit nitration in part 2.